Hi, my name is Yunjae. I'm in the Aerospace Engineering class of 2021, and my research advisor is Dr. Miller. I'll be presenting a theory that allows the hot film anemometer to detect a stall. Lift and the angle of attack are directly proportional to each other. The maximum lift by increasing the angle of attack is desirable for the maximum power generation in the wind turbine and the takeoff or landing in aviation. When the angle of attack exceeds the critical angle of attack, the significant amount of the lift reduces in a short time. This phenomenon is called stall in aerodynamics. This is very dangerous in aviation because the pilot cannot have a good control over the plane. Also, not efficient for the wind turbine because it doesn't know when the airfoil is having a maximum lift. To solve this issue, I propose a theory that allows the hot film anemometer to detect the flow characteristics and prevent the problem shown in the slide. A hot film or a hot wire anemometer is a sensor that measures the fluid speed based on the thermal analysis of the circuit. The electric current sent through the wire heats up the sensor up to 300 degrees Celsius. The wire is then cooled down by the fluid flow and decreases its temperature and resistance. The heat balance equation is then used to determine how much its resistance changes due to the flow speed. The basic principles of the operation for the hot wire and the hot film are the same, but the difference is the geometry of the sensor. The hot wire anemometer has many previously developed theories that shows its application. However, it is physically fragile and has an aerodynamic disadvantage when implemented on the airfoil. The hot film anemometer, however, can be implemented on the airfoil as shown. Multiple arrays of the sensor can be implemented on the airfoil, where each sensor measures the velocity fluctuation of their location. Then, the analysis of the gathered data is used to map out the flow characteristics. The difficulty of using the hot film anemometer is that it can conduct the heat through the surface, which significantly complicates the heat analysis. First, we make basic assumptions that underlie the thermal characteristics of the sensor. Second, partition the sensor into the several components that have similar thermal characteristics. Then, we can determine the heat balance equation of each component. Finally, combine the resulting heat balance equation to the governing thermal equation of the entire sensor. This method of derivation reduces the complicated heat balance equation of the hot film to the same form as that of hot wire system. Many of the hot wire anemometers theory are based on the governing equation as shown. Unifying the forms of the governing equations of both, we can apply hot wire theory to the hot film, thereby increasing the potential applications of the hot film anemometer. We can then make full use of both hot film's geometric advantage of the implementation and hot wire's theory of measuring the velocity fluctuation. Now we can sense the flow around the airfoil, which potentially makes the aviation safer and wind turbines more efficient. My research questions were to find out if it's possible to study the hot film anemometry theory side by side with the hot wire anemometry. Since freshman years, I always found the best part of the research is the one that allows me to explore the theoretical development of the sensor behavior. Therefore, in the initial stages of the project, I reviewed the numerous literature works on hot wire and hot film anemometry to gain more knowledge about them. Perry's hot wire anemometer book that summarizes the previously developed hot wire anemometer theories gave me the idea of directly comparing the hot film anemometry equation to the hot wire anemometry equation. I discussed with my research advisor Dr. Miller to narrow down many good potential hot wire anemometer applications. I love math and enjoy having deep focus by thinking of one problem persistently. Also, although I'm an engineer, I spend a lot of time understanding the detailed theory behind many engineering equations rather than just practicing its application. While intensively reading Perry's hot wire anemometry book, I wanted to try out if I could also develop a theory for the hot film anemometer. After completing this project, I am more certain that I enjoy working on theoretical development for the most. It is a fascinating experience to unravel such astonishing theories and completely devoting myself to a particular issue until I found the solution. I attempted 4 or 5 different methods of the derivation until I get a satisfactory result. It seems that every path of the derivation I believed it would work lead to the dead end. The truth is, sometimes the derivation seems to work very nicely at first, but leads to a more complicated equation and beyond my mathematical capacities. The more fundamental understanding of the sensor behavior and more mathematical tools I have, the more accurate and simpler the assumptions I can make. Based on my understanding of the sensor thermal behavior and many discussions I had with Dr. Miller, I'm confident that my theory would work, and I look forward to test it with the experiment. Thank you very much for listening to my presentation.